All right, good morning. On Wednesday, we talked about how boundary layers respond to a pressure gradient, right? And we particularly took an example and used that example to analyze how a boundary layer with three distinct layers respond to a favorable pressure gradient. This is a Desmos notebook that basically does exactly what we did in lecture. So this is basically how much the pressure has decreased. So a positive would be a decrease in pressure, and a negative would be an increase in pressure. So if you look at this, right? So basically we had exactly three layers in the boundary layer, and the free stream is velocity equal to 1. So that's an approximation of a boundary layer, right? And so we used this formula to compute how the free stream velocity u1 would have basically compute how the velocity in all the layers. So the u0 is actually a list would change as I increase the favorable pressure gradient. So as I make the velocity go higher and higher, what you see is that all the different layers of the velocity increases, and the layers where the velocities were smaller actually increases by a bigger amount, right? Because the increase in the square is actually exactly the same. And also because of conservation of mass, all the layers, as the velocity increases, the layers actually decrease in thickness. So overall, the thickness of the boundary layer, no matter which metric you look at, I think here I looked at, I printed out the delta 99, delta star, theta, and also h, the shape factor, right? Also, in the favorable pressure gradient, the shape factor actually would decrease. So if you look at h, in the beginning was before I apply any pressure gradient was 1.8, right? And I apply a favorable pressure gradient, the h not only does all the thicknesses decrease, but the shape factor, the ratio between displacement and the momentum thickness, also would decrease. So the trend is opposite if you add a adverse pressure gradient. So and finally, the skin friction coefficient actually increases, right? As opposed to the thicknesses decrease and the skin friction increases. So the increase in thickness and the decrease in thickness and increase in skin friction coefficient on the favorable pressure gradient is one of the things we'll look at on the airfoil today. On the other hand, when I make the pressure gradient adverse, which means I encounter a pressure gradient that slows down my velocity, the effect is exactly the opposite. So all the velocity layers are slowed down, and in particular, the originally slower layers sees a bigger impact, right? So see, like the free stream velocity is only slowed down by a little bit, the bottom layer got slowed down by a lot. And if you make it further and further, you're going to see the bottom layer is going to be slowed down almost to 0. And again, the conservation of mass makes sure that the velocity slowed down means the layers actually grow in thickness, right? And as a result of that, all the thicknesses would increase, and the shape factor would also increase to larger values, the ratio between displacement and momentum thicknesses. And also because the velocity gets slower, the layer becomes higher, right? The skin friction is proportional to the ratio of the velocity to the height at the bottom layer, right? So that skin friction would decrease as you are encountering an adverse pressure gradient. So this opposite effect of the thickness increasing and the skin friction decreasing is what we expect to see on the adverse pressure gradient. Again, that's something we'll see on airfoils. Okay, any question on this? So you see, like, you're gonna see all the formulas I have in the Desmos if you click the link on my notebook, right? So these are exactly what I used in lecture on Wednesday. And you are supposed to be able to understand the logic behind that and be able to replicate that for some different boundary layer profiles. All right. Okay. Now, finally, let's get to flow separation. So on this Desmos, what I want to show is that when you make the pressure gradient adverse enough, the first layer, the bottom layer, is going to become essentially zero velocity, and as a result of mass conservation, infinity in height. That's actually when flow separation is going to happen, right? And let's actually watch a video that actually experimentally shows how flow separation happens and what exactly flow separation looks like. And this afternoon, if you come to the lab sessions, we'll use a computational fluid dynamics example to also illustrate how flow separation actually works. Do I have audio? Yeah, so this is flow separation starts to happen, right? So you're going to see that the sum of the velocity now becomes negative, and essentially there forms a recirculation region where initially the flow is completely attached, and as the angle of attack increases, the recirculation region forms, right? So essentially at some point, the velocity close to the boundary becomes almost zero, right? As a result, the thickness of that layer goes up to infinity. Of course, that is not really going to infinity, but like the shear layer, the boundary layer, basically moves away from the wall, and the region between the wall and the shear layer that separates from the boundary forms a region that we call recirculation region, where the flow has very low velocity compared to the free stream. Okay, so that's something else, right? Okay. Yeah. So the flow separation really determines what is the maximum lift an airfoil can obtain. So this is because as soon as the flow separates, the region, you can think about the flow separation as if the boundary layer becomes so thick that the thickness of the boundary layer, the region between the separated boundary layer and the airfoil itself, is comparable in size to the chord length, right? Okay, and as a result of that, as if you trace both the bottom of the airfoil and the shear layer that separates, the airfoil behaves as if it has a super thick trailing edge, right? The trailing edge is now as thick as the distance between the shear layer that's separated and the actual trailing edge. So the effective angle of attack of the airfoil, now instead of being the real angle of attack of the airfoil, gets decreased by almost half of the effective thickness, right? And that basically reduces how much lift you have on the airfoil dramatically. So most of the time, when an airfoil achieves maximum lift, it is when flow separation started to happen, but haven't been so, the shear layer hasn't been so far away from the trailing edge yet that it decreases the lift significantly. So this is the kind of different airfoils that achieves various maximum lift on the different Reynolds numbers. And we'll see in a moment, especially for these low Reynolds number airfoils, what actually happens. And on the high Reynolds number airfoils, we have to wait until I think next week or the week after next week, when we start to understand the turbulent boundary layers, to be able to reason why these higher Reynolds number airfoils has almost like a different behavior on the front part and on the later part. Okay, and similarly, like lift to drag ratio. So this is even more difficult. So not only you have to reason about how much lift you get, you have to also manage how much skin friction and drag you have on the airfoil. Okay, so let's first do a little bit of starts to reason what's happening on the airfoil. Okay, so let's first look at the symmetric airfoil on the different angles of attack. So a thin and symmetric airfoil at 0 degree angle of attack, the pressure coefficient we have looked at several weeks ago follows the middle line, right? And when the airfoil is thin enough, both sides of the airfoil behaves almost like a flat plate, right? Where the pressure gradient is 0. So this is roughly 0 pressure gradient. There is a little bit of a pressure gradient that is going down in this line. So going down in this line means adverse or favorable pressure gradient. Somebody think about it. Adverse means the pressure is pushing against the flow, right? Yes. Should be adverse, exactly. So we're looking at CP here, right? As the line goes down, it means CP increases, right? As I travel downstream. A pressure increase as I travel downstream means the pressure gradient is pushing against the flow, right? So the line going down means adverse, line going up means favorable, okay? But it's almost zero, almost a zero pressure gradient. So we expect the boundary layer to behave almost like a flat plate. And we did the analysis on the flat plate, right? The thickness of the boundary layer goes like square root of x, right? So we should expect to see something like that. Okay, now as the airfoil is under a finite angle of attack, so let's look at the 2 degree case. And this is all inviscid pressure distribution, okay? The bottom pressure goes like this, and the top pressure goes like this. Well, the bottom is not that different from the 0 pressure gradient case, right? So there is a region, maybe going from 0 to 20%, over which the pressure is, the CP plot is going up, which means what kind of pressure gradient? Favorable, right? And then it's almost flat. But the top is more interesting. The top has a extremely high favorable pressure gradient, almost right at the leading edge. But then it follows a very strong adverse pressure gradient, which gets less strong but still negative all the way to the trailing edge. So let's think about what this means in terms of thickness and also skin friction coefficient. Okay, so in terms of thickness, let's start from the bottom edge. Over the favorable pressure gradient, thickness should what? Would the thickness on the favorable pressure gradient be smaller, thinner, or thicker than if there is no pressure gradient? Thinner, exactly, right? So on the bottom layer, we should see a boundary layer that is relatively thick, right, compared to the 0 pressure gradient case. Okay, but on the top layer, what happens is that you get an extremely favorable pressure gradient. So at this point, at this peak suction, or peak, the minimum pressure point, we should see a boundary layer that's extremely thin, right? Okay, so it's actually very useful to understand exactly how thin the boundary layer is going to be over here for the purpose of computational fluid dynamics. So if you want to do computational fluid dynamics, you have to make a mesh that discretizes the space occupied by air, right? And you need to understand how thin the boundary layer is to choose actually around the airfoil how thin you want the first layers to be in order to capture the boundary layer. So it's actually quite useful. We'll not do it today, but we'll do it probably next Friday, and to estimate how thin the boundary layer is going to be at this point. But starting from this point, you get a long and consistent adverse pressure gradient. So you do expect the boundary layer to become thicker and thicker and thicker and thicker, right? So this is actually something we looked at last Friday. The boundary layer at the trailing edge is quite asymmetric, right? On the bottom, the boundary layer is actually much thinner. On the top is much thicker. And as a result of that, right, the airfoil is effectively at the lower angle of attack than these 2 degrees, right? So viscosity, the effect of the boundary layer, the effect of the boundary layer being asymmetric, and therefore displacing the free stream, displacing the inviscid streamlines out of the boundary layer in an asymmetric way, makes the lift coefficient go not proportional to 2 pi times alpha, but slightly lower, right, for very thin airfoils. Yes?
I didn't get why there's a very different thickness on the trailing edge at the bottom and at the top, because the pressure gradient seems really similar between those, like top and bottom of the curve.
Yeah, so the pressure gradient, they are qualitatively similar in the sense they both follow favorable and then an adverse pressure gradient. But the magnitude is, the magnitude of the adverse pressure gradient is very different, right? So, so that relates to the kind of the combination of pressure force and viscous force. The viscous force is going to make the boundary layer go thicker, right? And it is dominant, especially when the boundary layer is very thin. So at this very tip of the suction peak, although there is a very strong favorable pressure gradient, but viscous force is going to make the boundary layer not going to be infinitely thin, right? Then starting from here, you get a consistent and large magnitude adverse pressure gradient, and that adverse pressure gradient is a lot stronger than the adverse pressure gradient suffered by the bottom layer, right? So as a result, the top layer is going to have a much larger thickness. Okay. And also, if you look at the skin friction plot, the skin friction peaks over here, but it's going to become lower and lower, and it's going to be actually lower. The skin friction on the upper side is going to be lower than the lower side towards the trailing edge, if they both don't transition or if they both transition to turbulence. We'll look at it later. So the picture is quite different if you look at a different airfoil, like a thick airfoil like that, right? So on the thick airfoil, even at 0 degree angle of attack, the upper and lower side is different. Again, qualitatively it's the same. The pressure both decreases and then increases. So you have favorable and then adverse pressure gradient, right, as in the previous case. But the magnitude, again, even at 0 degree angle of attack is different. So here you see the maximum suction is over here. It's almost, it's not as sensitive to the angle of attack, right? It's always going to be around this point. So you always have favorable pressure gradient over along this side, and adverse pressure gradient over here. And then if you look at the maximum magnitude of the adverse pressure gradient, how big the gradient is. The maximum magnitude on the thin airfoil is around the leading edge, right? And the maximum adverse pressure gradient for this airfoil is around the trailing edge. So all of these can be actually predicted qualitatively using thin airfoil theory, right? We have looked at thin airfoil theory, and we have seen that for the thin airfoils, the pressure lines, the pressure difference, right? They follow closely to what's predicted by thin airfoil theory, all the way to very close to the leading edge. This is because it's very thin, right? And the thin airfoil theory predicts the pressure difference goes to infinity, so you have a very high peak over here. And for thick airfoils, the thin airfoil theory still qualitatively predicts what's the pressure difference on the upper and lower sides, but the discrepancy is over a larger region around the leading edge. So you don't see the huge peak, even if you put it at higher angle of attack. And also the difference at 0 degrees angle of attack can also be predicted from the camber line of the airfoil, which is not going to be 0. Okay, so so thin airfoil theory is going to tell you where you would see a very adverse pressure gradient, which is going to tell you how the airfoil is going to separate, right, when you put it at a higher angle of attack. So for example, for the airfoil up there, you expect the flow to, as you put it at higher and higher angle of attack, you expect the flow to separate over here, right? Here is the maximum adverse pressure gradient, while for this airfoil over here, you expect the flow to separate, starts to separate towards the trailing edge. Right, so that's all the effect of adverse pressure gradient. All right, so this is a illustration of how the boundary layers are on the different adverse pressure gradients, and as a result, the thickness becomes quite different. So the blue is the upper side, and it becomes much thicker. So this is for a very low Reynolds number, 50,000, right? And here you can see the thickness of the boundary layer is actually comparable to the thickness of the airfoil in this case. So you do expect how the lift coefficient changes as the angle of attack increases is going to be significantly affected by viscosity, right? Okay, and on the other hand, this is at a much higher Reynolds number, a milling. You can still see a quite different thickness at the trailing edge, and of course this is at a much higher angle of attack. The flow would have separated if you put this airfoil at 9 degrees angle of attack, but for a higher Reynolds number, the flow actually transitions into turbulent boundary layer pretty far upstream, and so the turbulent boundary layers are much more resistant to separation, and as a result, you haven't separated all the way at the end. Okay, so we'll discuss turbulent boundary layers more next week. All right, and yes, again, this airfoil, I think we can file up Xfoil and do some demos over here. If you use a very thin airfoil, and if we just use a milling Reynolds number, so 0 degrees is the same as what I've shown in the notes, and if you put it at a higher degree, higher and high angle of attack, it's right, it's starts to not converging, but like the reason it's not converging is that you can see the flow starts to separate very close to the leading edge, and Xfoil basically doesn't really solve for post stall conditions. So as soon as the stall, like massive stall starts to happen, like it often just fails to solve the flows. So the thin airfoils, they separate towards the leading edge. But now if you look at the thick airfoil with a very strong camber towards the trailing edge, so 6618, 18 makes the airfoil pretty thick, and 6 has a large camber, and the other 6 means the maximum camber is towards the trailing edge, is over 50%. So that's a recipe for the pressure gradient to be very adverse towards the trailing edge. So even if you put it at 0 degree angle of attack, you're going to see the adverse pressure gradient, right, is mostly towards the trailing edge. And if you put it, starts to put some angle of attack onto this, you're going to see here is flow separation already happening, but towards the very trailing edge, right? So here a significant effect is you see this boundary layer just grows in thickness very rapidly, and the pressure becomes almost flat, right? So what angle of attack did I put it in? So if you put high angle of attack, you're going to see the separation just keeps moving slowly upstream, and it's just a very slow process. So this type of separation from the trailing edge is actually a lot more gentle, right, as you can see, than the sudden flow separation from the leading edge. So if you want a very controlled stall, right, where you don't have a sudden jump in your lift coefficient and the moments, this kind of thick airfoils with a large camber towards the trailing edge is a good option. Okay, so these are with how airfoils stall. So let's actually start to look at like what's let's start to look at some of the more quantitative aspects of the boundary layer, and particularly if we want to understand that, the transition to turbulence actually matters a lot. So all what we have discussed so far, right, is the viscous forces regarding to what we call like a laminar boundary layer. And for turbulent boundary layers, so let's first take a look at a flow visualization of a turbulent boundary layer to get a sense of what turbulent boundary layer is about. So in laminar boundary layers, we have always assumed that the flow is steady state, and turbulence is all about unsteady, right? So let's actually take a look at what a turbulent boundary layer, how does it become unsteady as the boundary layer grows. Okay, so let's actually start from the beginning. So we have a camera here that traces the boundary layer not at a fixed point but moving downstream. So we basically observe how the boundary layer grows as the camera is moving downstream. So initially we see a laminar boundary layer over here that has very little eddies, right? And as you go downstream, that's the 0.0 location is when the flow transitions into a turbulent boundary layer, and you're going to see the flow becomes quite unsteady afterwards. Okay, so here is what you start to see in a turbulent boundary layer, right? So there are all kinds of eddies in the boundary layer that moves some of the fluid into closer to the wall and move some of the fluid further away from the wall, right? So the structures you see are actually pretty typical of a structure in what we call a shear layer, right? So if you watch the clouds, sometimes when the different atmospheric layers are moving at different directions or different speeds, you see similar patterns like this. So all of these eddies, if you observe carefully, some of them are moving down, some of them are moving up, right? As a result of these relative movements, the eddies that are moving up towards the wall brings some of this high momentum fluid that's further away from the wall into closer to the wall. And the eddies that are moving down bring some of the slower fluid, the fluid that are more stationary relative to the wall, into the faster streamlines. So this kind of mixing in momentum is what is the number one thing that makes a turbulent boundary layer behave differently from a laminar boundary layer. So let's actually observe it a little bit further, right? So as you go further and further downstream, the boundary layer thickens actually more rapidly than a laminar boundary layer. And the reason of the more rapid thickening is actually exactly because of the momentum exchange, right? So if you have eddies moving down, that brings the slower fluid closer to the edge of the boundary layer. That is a significant source of slowdown of the edge of the fluid at the edge of the boundary layer. That contributes to the growth of the thickness, right? Okay, so these are all qualitative. We are going to put this into a bit more math later on. All right, and another thing you see is that the size of the eddies are actually different in different regions of the boundary layer. So closer to the wall, you don't really see very large eddies, right? And that's actually because closer to the wall, there cannot be large eddies. A large eddy would actually go into the wall, right? But the further away from the wall, the distance from the wall actually would allow larger scale eddies to be happening. And of course, the larger scale eddies is more effective in moving flow, right? So a larger eddy would be moving flow from deeper close to the wall to further away, and moving fluid further away into deeper at the wall. So a larger eddy further away from the wall is more effective in transferring different the momentum in different regions. So these are so first of all, these eddies transfer momentum, and the bigger the distance is from the wall, the bigger these eddies are, and the more effective these eddies are transferring momentum is the two important things we need to understand about the mechanism of the turbulent boundary layer. Okay, any questions on these movies? Okay. So let's actually also look at what's happening on the airfoil, right? So the airfoil is it's very similar to the plot we have seen before, but this is basically illustrating how these movies are generated on this airfoil. So again, the boundary layer actually in this case is forced to transition into from laminar to turbulent boundary layer by placing a tripwire over here. So tripwire is just a small obstacle in the boundary layer that introduces unsteadiness so that the boundary layer transitions. Okay, and then you can see like all these eddies being very clearly visualized by these dye in the fluid. All right. Okay. So let's actually. There is also turbulent boundary layer on the wing. So let's just also take a look at it briefly. And this, instead of an experiment, this is a what we call a direct numerical simulation. So it's a computational fluid dynamics calculation. The results shown here are not pictures observed in experiment, but that comes from a computational result. And the simulation domain is not the entire airplane, but just a small fraction of the wing itself. And this is the kind of a mesh that is required to do this kind of calculations. Again, this relates to, for example, if you need to understand how thin the boundary layers are in order to decide, right, how fine of the mesh you have to make. Right. Yeah, so this is a colorful illustration of all these eddies in the turbulent boundary layer. And yeah, again, like the movie is. All right, I think there are plenty of this kind of pictures you can watch, but let's start to understand a little bit more quantitatively what's the primary difference between a turbulent and a laminar boundary layer. And to do that, we first have to understand a little bit more about the effect of viscosity. And let's start from laminar boundary layers and look at what would be different if the boundary if the problem is turbulent instead of laminar. Okay, so first of all, let's think about a laminar problem. So we have the flow between just the two plates. Okay, and the bottom plate is stationary and the top plate moves at the velocity of, let's say, v naught. And there is no pressure gradient or anything in the entire problem. So there is only viscous force. So the question is, what is going to be the velocity profile? Velocity, which is it's not a function of x, right? In the x direction, everything is translationally symmetric. So the velocity profile should only be a function of 1. So in this case, I want to ask you, based on our understanding about the viscous shear stress, right? How should the velocity as a function of y be like? How do you start reasoning about this problem? Yeah.
Because if you consider like a layer of top, viscous force from the top should balance the viscous force from the bottom. Otherwise, it'll accelerate
Yes.
or decelerate, and then that violates our initial assumption.
Yes. That's a very good starting point. Is the balance of forces, right? And the only force that's affecting the fluid over here is viscous force, right? Okay, so again, like what you said, if you look at a layer of fluid, and consider momentum balance, there is force that's dragging the fluid downstream from the top. There is force dragging the fluid upstream from the bottom, and then there is no pressure force, but there is momentum flux. There is momentum flux going in, and there is momentum flux coming out. Fortunately, because the flow is not a function of x, right? So the momentum flux going in is always exactly equal to the momentum flux coming out. Okay, so that we can ignore. That means the force on top and force below should exactly balance out. Yes?
Again, why is the force not a function of x? Is it just because we're zooming into a really small?
Yes, we are looking at a translationally symmetric problem, right?
Oh.
So we have an infinitely long plate above and infinitely long plate below. So that's and in reality, it's approximately true if the plate length is much larger than the space in between them, right? So that ensures that the flow is not a function of x.
But why do we have two plates?
Or
is it only one?
There are two plates. I'm just making up a problem to illustrate the difference between a laminar flow and a turbulent flow, right? Okay, so here we are first considering a laminar flow because this is the simplest problem where you don't have to consider any momentum flux difference. You also don't have to consider any pressure forces. And in order for us to not consider these, the simplest setup is to have two plates, two walls, one above and one below. Yeah.
So to be clear, it's just the top plate moving.
Yes, it's just the top plate moving. The bottom plate is stationary. Yeah. Okay. So now, what are the two forces? Again, like viscous force per unit area, tau, right, is equal to what? So this is viscous force per area.
It's viscosity mu.
Yeah.
Times du over dy.
Exactly, dux over, I think we said dvx over dy. That's right. Okay, and we have drawn a control volume where the top area is equal to the bottom area, right? So the force balance essentially just says that the tau at the top is equal to tau at the bottom. And the viscosity is the same, right, for fluid, which means that the dvx dy at the top has to equal to dvx dy at the bottom. Or the derivative, the slope, is constant, right? So this is equal to a constant. And we know the slope is constant, and we know the velocity at the bottom to be 0, and we know the velocity at the top to be moving with the wall, v0, right? And that completely tells us what the velocity profile is. Okay, that means my vx of y has to be if this is y at 0 and this is y at b, right? Then the velocity profile has to be v0 times y over b. Right, that's the only linear function that satisfies both vx of 0 equal to 0 and the vx of b equal to v0. All right, agreed? Okay. Now let's imagine, instead of having a laminar flow here, what if we have a turbulent flow? What if we have not just have a shear stress, but also momentum transfer, right, by all these eddies from above and from below, by these eddies that brings fluid in and out of basically up and down, right? Something we just saw in the previous slides. And also another thing we know is that so basically there is additional momentum transfer. So in previously in laminar case, I have tau of at y1 equal to tau of y2, right? I mean, imagine this is y1, this is y2. Okay, and for the turbulent case, I still have tau of y1 that's moving the fluid, moving the control volume downstream. But then I also have additional momentum transfer from the eddies. And let's just call this momentum transfer from the eddies as tau t, turbulent, called like turbulent shear stress, is equal to tau at y2 plus tau t at y2. Okay. Now let's think about what is the trend of tau t? How does tau t depends on both the distance of y from the wall and also what is the velocity gradient? Okay, so what I can say is that tau t is an increasing function of two things. One is distance from wall, right? Because the further away I'm from the wall, the larger the eddies are, right? And it is more effective in transferring momentum. It is also a function of dvx dy, right? Because these eddies, they transfer momentum over a distance. And the derivative of velocity over dy determines like what is the difference of velocity like just above the eddy and below the eddy, right? So these eddies are mixing different velocities, but how different the velocities are depend on how basically depend on dvx dy times the size of the eddy. Right. Okay. So basically, what I can say is that the turbulent shear stress, which is basically how much momentum transfer per unit time per unit area is due to these eddies, is an increasing function of these two things. Okay. And let's just make a very simple model. So let's just make it a simple model, being a constant times the distance from the wall times dvx dy. All right. So if we make this simplifying assumption, and then let's look at how the velocity profile is going to behave. Okay. So then what we have is we have first of all the laminar term u times dvx dy plus a turbulent term c times the distance, which is going to be the minimum of y and d minus y, right? So that's the distance to the wall times dvx dy. That has to be a constant, right? Because still the shear stress above and below has to balance, and that's for any control volume over any y1 and y2, right? So basically the summation has to be a constant. All right, and both terms has dvx dy, so let's just add them up. So mu plus c times the minimum of y and d minus y times dvx dy has to be a constant, which means dvx dy has to be inversely proportional to this. And let's draw what this function is as a function of y. So let's say this is y, 0, and d, and this is my mu plus c times minimum of y and d minus y, right? So we know this is always being above mu, but And at 0, when y is equal to 0, this is exactly equal to mu. And when y is equal to d, this is also exactly equal to mu. And as y goes towards the middle of this channel, this function becomes the biggest. So this is how the coefficient behaves as a function of y. Okay, and as a result of that, dvx dy is reciprocal, is proportional to the reciprocal of that. It's going to be a function like that, right? Okay, which means the derivative of velocity is going to be the slowest at the center and largest at the edge, right? So now if you draw a velocity profile of a turbulent channel, what would it look like? It is going to look like that, right? Agreed? The slope has to be small in the middle and the larger at the edges. Okay, so this is one of the simplest scenarios of how turbulence, right, of turbulent mixing of the different momentum layers is going to change the velocity profile. Okay, and let's actually look at another case that's more widely studied. Okay, so that's a viscosity, a combination of viscosity and pressure. So let's again first look at a laminar case and then look at how, in this case, the turbulence is going to change the velocity profile. In this case, we have a constant pressure gradient. Gradient of P is going to be always aligned with the negative x direction. Okay, is going to be, let's just say, minus ex, right? Which means pressure, you can think about pressure being a constant minus x. So is this favorable or adverse pressure gradient if you think about that as a boundary layer? It's favorable, right? As you travel downstream, in the x direction, the pressure always is decreasing. Okay. Now, how would this flow behave in terms of its velocity profile if we only have laminar flow? How do you think about that? Again, we are assuming these walls are parallel for infinitely long, so that the velocity profile would not be a function of x, right? Although the pressure is a function of x, but if you write down the equation, the velocity only reacts to pressure gradient, right? So the pressure gradient being a constant means, and the geometry being constant along x direction means the velocity profile shouldn't be a function of x. Now, how do you think about that? How do you determine the velocity profile? Again, we want to compute the ux as a function of y. Yeah?
This is non-zero. Because you can do the same thing as before, proving that it is linear, but then you have b at 0 equals 0 and b at h equals 0, so it should be at 0.
Should it be 0? Okay. Yeah, that's a very good argument. I can do the same thing as I did before, right? I can draw the same kind of control volume, right, as before. So I can draw a control volume. I have y1, y2, and I have shear stress above and shear stress below. And also the momentum flux from left and from the right is actually the same, right, because velocity doesn't depend on x. But how about pressure force? Do I have the same pressure on the left face or right face? No, right, because the pressure is a function of x. So I have higher pressure on the left than on the right. That creates a force in which direction? Downstream, right? So let's say this is delta x, and my pressure force, is equal to, let's say I have a span-wise extent is b, right? And the pressure force is equal to y2 minus y1 times b times my pressure gradient, which is equal to 1, so times delta x, right? That's how much pressure force I have. Okay, so now my pressure force has to be balanced by the difference of the viscous forces, right? Which means the difference between the viscous forces above and below cannot be zero anymore. All right, so that means my tau times area b delta x from above, from at y2 minus my tau times b delta x at y1 has to equal to the pressure force, y2 minus y1 b delta x, right? Okay, and b times delta x doesn't depend on y1 or y2, so it's basically the tau, right? So tau is equal to mu times dvx dy. I can just write y1 minus y2 times b delta x, and b delta x cancels over here, so it's just equal to y2 minus y1. All right. Now we get something a little bit more interesting than on the last slide. Instead of the derivative of velocity being a constant, the difference in the derivative over a distance is equal to that distance itself. What does that mean? Right, so the derivative itself is a function, right? If that function, if the difference of that function between two values is proportional to that the difference of the y, what does that mean about that function? Yes?
The derivative is linear, so the actual function should be quadratic.
Exactly, the derivative is linear, right? So basically, if I divide both sides by mu, right, that means this dvx dy, right, is actually a linear function of y, and only a linear function, right? With a let me see. So this is dvx dy as a function of y, right? Only a linear function can have that the difference between the function values is proportional to the difference between the y's. Okay, good. So we know that dvx dy is a linear function, and we also even know what is the linear coefficient is 1 over mu, right? That means Vx is quadratic, and with a curvature of 1 over mu. So we'll come next lecture and exactly construct this quadratic function, and then look at how turbulence would modify this quadratic function into something else. All right. And with these two examples, we should be able to understand what's the primary difference between a turbulent and the laminar boundary layer and its consequences. Cool. Thank you.